Okay, we're going to solve a differential equation in this example using the Cauchy-Euler Theorem. Now I cheated and I put an abbreviated version of the theorem at the top there. Let's see, I am missing the part that says x has to be bigger than 0. That doesn't affect us too much as through our work. And actually I should probably make the arrow go that way, because if we're able to solve this, we have the solution to this. But I'll leave it like it is. So we do have a Cauchy-Euler equation because we've got x squared and a y double prime, x to the 1 and a y prime, I left that prime off, plus a constant times y, which is just 1, equals a function of x. So our f of x is 2x. And recall, once we solve this, the equation that looks like this, we're going to have a function of t, and we're going to have to use these substitutions here to get rid of the t's and bring x's back into play. So x is e to the t, which means t is ln x. So for the Cauchy-Euler theorem, I want to prove, let's see, it'll be d squared y dt, and the coefficient is a 1, minus, well, let's see, let me go ahead and write a is a 1, b is a -1, c is a 1. This is b minus a, so it's going to be -1 minus 1, which is going to be a -2 dy dt plus y equals not 2x. We're done with x's for the time being. X is e to the t, so 2x is 2 times e to the t. So this is the equation that has constant coefficients that we're going to solve. So we're just going to do we're going to do it as usual in 2 steps. Let's find the homogeneous solution, which means we get the characteristic equation m squared minus 2m plus 1 equals 0. We solve that. And let's see, if we factor that, we get m minus 1 squared equals 0. So m equals 1, but twice. Remember that? So it's not exactly the same as our previous examples, but we do have the solution. It's y homogeneous is equal to the constant 1 times e to the t. Why is it e to the t? It's e to the 1t, because this is 1. Now we don't say c2e to the t. Remember that? When you have identical factors, you have to put another t in front of it. So that was simple. We got our homogeneous solution. And I'm going to use the method called the variation of parameters. You may have to go back and look in your notes, where we'll use the homogeneous solution to come up with a particular solution that works. So what I need to do first is compute the Wronskian, the determinant of the 2 by 2 matrix, which takes, you have a constant times a function plus a constant times a function. So I've got 2 functions, e to the t and te to the t. And in the second row, we take their derivatives. Now, the first one's easy, e to the t, and the second one is t e to the t plus e to the t. So if we take this determinant, remember, it's like AD minus BC, where we have A, B, C, D. Those 2 minus those 2. We get e to the 2t. So our Wronskian, the determinant of this matrix right here, is e to the 2t. And we're going to use that to figure out our particular solution. So I'll make a note. By variation of parameters, and I'm not going to write the generic formula down, I'm going to dive right into it. So you can go back and look in your notes if you need to. Our particular solution, I'm going to go ahead and put of t to remind myself, although I'm going to have t's on this right-hand side, that this is not our final answer. We need eventually to get a y particular of x. So y particular of t is going to be e negative e to the t, this guy, times the integral of the other one, t e to the t, 2 e to the t, divided by the Wronskian. 2e to the t on top came from this guy. Just to refresh your memory, this should be e to the 2t here. This e to the 2t came from the Wronskian, the denominator. So we're not done yet. dt plus t e to the t. Let me make that plus so it doesn't look like a t. T e to the t times the integral of e to the t 2e to the t over e to the 2t dt. Okay, and that's equal to, I'm going to write a little bit smaller now, negative e to the t times the integral of. Well, notice that e to the t times e to the t is e to the 2t. That's gone. That's the integral of 2t dt. That's simplified greatly. We're not done with the integral yet, but it looks a lot nicer now. Plus the t e to the t times this integral, which e to the t times e to the t is e to the 2t, which cancels with this, just the integral of 2 dt. This is equal to negative e to the t squared plus t e to the t times 2t. This plus is that plus. This goes with that, and this goes with that. Equals, I'm going to go over to the right, t squared e to the t. All right, so our particular solution is this. So if we've got YH, our homogeneous, and our, we need to do some converting back, but let me go ahead and write y, the entire y, in terms of t. Let's see. I'm running out of room, so let's go for the final answer. Y is equal to, let's see, x is e to the t is ln x, so notice what we're going to get here. E to the t is e to the ln x, and remember that e to the ln x is equal to x, so we're going to use that throughout this substitution. So we've got c1x. So let's just double check that. T squared, I'm going to have to do this in 2 steps. Let me do some simplifying with the t. Let me write down the whole. We've got c1 e to the t plus c2t e to the t plus t squared e to the t. This is the equation that we're almost done. We just need to convert that one to use x's, so we need to do the substitution. So I'm going to get y is equal to c1. Here's where I get the e to the t, but t is ln x, so I get e to the ln x, so that's an x. Plus c2, same thing, this will give us an x, and the t is ln x, so x ln x, we use this for that t, and this e to the t is just x. And for the last one, we get e to the t is e to the ln x, which is just x, we knew that. And t is ln x, and then we need to square that. And that's the final solution. Now, don't make the mistake of calling this ln x squared. It's ln of x squared. It's not the natural log of x squared. Okay, so that one took a little bit of simple calculus, substitution, a lot of algebra, but that wasn't too bad.